All right, guys. So in this platform, we are going to consider the question paper that we wrote in April 2024 exams so that we can have a revision and see how we are supposed to attempt these typical questions that we are given. So make sure, as usual, go through the instructions that you are given. That is the information that is to understand what you are given throughout the question paper. So there we do not have much there to consider. So guys, let us quickly rush through our questions. So the first part we were given on question number 1, which is the movement, energy, and power. Various options are given as possible answers for the following questions. Choose the answer and write only the letter A to D next to the question number that you're given in the answer book. So that is your instruction. So the first part we are given, the tendency of an object to remain at rest or continue in its uniform motion in a straight line is known as what? The tendency to that. Remember, that is our inertia. So the tendency of an object to remain at rest or continue in its uniform motion in a straight line, that is your inertia. So it's actually, this is the definition of your inertia. They can ask you to define that. You're supposed to be able to define that inertia. Acceleration due to gravity on Earth is greater than that on the moon. That is what you're given. The acceleration due to gravity. Remember our gravitational acceleration. So they are saying on Earth, it is greater than that on the moon. Which one of the following statements is correct from what you're given? So in this case, we're supposed to analyze the statement and see if it does make sense according to what we are given. All right, the first part we are given, the weight of an object on Earth is the same as that on the moon. All right, let's talk of weight. Remember that the weight is equivalent to mass times the gravitational acceleration. And there we are given that the gravitational acceleration, it is greater, that one on the Earth. It is greater. So the moment you have a bigger value here, it means they're not going to be the same. The weight that you're going to have on Earth is going to be more than that of the that you're going to have on the moon. So meaning to say this statement is wrong. We want the one that is correct. So this one is wrong. Let's move on to B. B, we are given the mass of an object on Earth is greater than that of the moon. Okay, this is wrong. Remember, when you're talking of the mass is not affected because you are on Earth or you're on moon. What is affected is the gravitational acceleration. So this is not true. But if we check on C, the mass of an object on Earth is the same as that on the moon. This is actually correct. The mass is not affected. If you are on Earth, your mass, you are not talking of the weight, the mass, not the weight. Then D, we are given the weight of an object on Earth is less. It cannot be less because we are given that it has a greater gravitational acceleration. And to this, I said it must have a greater weight. So meaning to say this is wrong because they're saying it's less. So D is also wrong. So the correct answer in this case was going to be C. In terms of the mass, we have got the same mass whether you're on Earth, whether you are on the moon. According to the Newton's second law of motion, the acceleration of an object is, what is it referred to? Its mass, comparing with the mass. All right, this is inversely proportional to the mass that is gonna be on D. Remember, it is directly proportional to the force that is given, but when it is to the mass, it is inversely proportional. All right, then we consider on 1.4, when the velocity of a moving object is doubled, you double the velocity. The object, okay, then we are given here, the object is doubled. What is doubled there later on? Okay, let's check the net work done. All right, is it that the work done is going to be doubled? Let's see. The work done, remember, that is force times distance when you're given the part of the distance, the displacement. As this velocity is doubled, it increases this displacement. Not to say it is going to double, but it just increases the value of what? Of the displacement. Not to say it is going to double. So this does not correspond to what we are given. So in this case, there is nothing to compare with our velocity there. There is nothing that we can use to say it has doubled. So this is not true. The kinetic energy, all right, let's talk about the kinetic energy. Remember, that is half mv squared. So the moment that you double this velocity, it does not affect this kinetic energy being doubled, because that will be something else in terms of the kinetic energy if you double this. So that does not affect, because remember, there's a square there. There is a square. So meaning to say the kinetic energy is not affected. What about the potential energy? Remember that the potential energy is given as mgh. We do not even have velocity, so there's nothing to compare with the velocity in this case. The linear momentum, remember that the momentum being the product of the mass and the velocity, what it means is that this mass is a constant. So it follows that the momentum varies directly as the velocity that we are given. It is directly proportional. It is directly proportional. So if you double this, it means this also will be doubled. That is the condition. They are directly proportional. So in this case, we are saying the momentum is the one that is going to be doubled. So that is the correct answer there was going to be on D. All right, then let's consider another question, 1.15. An object is projected upwards and air resistance is ignored. We are not considering the air resistance. It is projected upwards. As an object rises, as this object is going up, its velocity, what is going to happen with the velocity? Okay, let's see the first part. Its velocity and acceleration are both directed upwards. Okay, we are talking of the acceleration in this case. And what type of acceleration are we talking about? That is the gravitational acceleration. As you are going up, remember, the gravitational acceleration opposes in the other way to be a negative. So meaning to say this will be wrong, because the acceleration is going down. Okay, the acceleration are both directed downwards. Okay, this is wrong because you are going up, acceleration is downwards. We are given it is directed upwards. That is the velocity, directed upwards, but its acceleration is directed downwards. That is exactly what is happening, because you are going up, but you are opposed due to gravity. So this can be the best answer. All right, is directed downwards. The velocity cannot be directed downwards because you are going up. So this makes it to be wrong. Before we talk about anything, this makes it wrong. And also acceleration upwards. This is also wrong because you are opposed due to the gravity. So the best answer there was going to be on C. So that is what we had on the first question, or the first part of our question. Then we are given 1.2. A car travels at 3 meters per square second, which is the acceleration from rest. Okay, for 30 seconds, it is in an easterly direction from F to G. And also, okay, let us just have a sketch of what they are trying to say here so that at least we can understand this information. So we're just gonna have a sketch in this case. So when an object is being accelerated, considering our velocity time graph, we are going to have something of this nature, our velocity and time. So it is accelerated from rest, meaning to say from the initial point at this point from rest. Accelerated means that there's an increase in terms of what? In terms of the speed. So there's an acceleration during this first phase for 30 seconds. So that is going to correspond to the time at 30 seconds. We are given this is taking in an easterly direction from F to G. This acceleration here occurred from point F to point G. So from point F to point G, that is where our acceleration happens. So this is your acceleration, 3 meters per square second. Remember, you started from the initial point where your initial velocity there is 0 meters per second. If you want to write this, it's fine. 3 meters per square second, the time, which is 30 seconds. Then from there, from G, it travels at constant velocity. The velocity is constant. We do not know this velocity that is at this point. And if we are to consider, they never talked about that. And somehow you see that you need to have that velocity. So let's just finish up about this velocity. How can you calculate this velocity at G, which is the final velocity when this car was accelerating? We know that acceleration is simply the change in velocity over the change in time. So meaning to say this acceleration is equal to the velocity that we do not know at this point over the time which was taken between this point. So we can even cross multiply and find our velocity, which is 30 times 3, that is 90 meters per second. So at this point, this velocity is at 90 meters per second. Remember your velocity in meters per second. Or you can use the laws of your linear motion. V is equal to U plus AT. So meaning say V minus U. Okay, so we need V there. So just going to substitute our U, the initial velocity, which is at 0 plus the acceleration, 3 times time, which is 30. So still we're going to obtain the velocity of 90 meters per second. That is the velocity at this point. So this is the one they are saying here. From G, it travels at constant velocity for 2 minutes to H. From the point G, it is moving at 90 meters per second. The constant, meaning to say there is no change in velocity. It's a straight line from the point G to point H. But this happened within 2 minutes, according to what we are given, 2 minutes. But this is time which is measured in seconds. But in within here, we've got 2 minutes. So meaning to say we are going to convert this time to seconds. 2 times 120, 2 times 60 to obtain 120. Remember, 1 minute, that's 60 seconds. So meaning to say from this point here, where there is a constant velocity, we covered 120 seconds. So if you add, we can even have the velocity at this point after at point H, which corresponds 120 plus this 30, that is 150. All right. So that is the time at point H. And then we are given, and then it starts to slow down and stop, meaning to say there is no movement. When it stops, it is now at 0 there on the ground, just like what happened here. There is no movement. So we are going to have it on the ground. There is no movement there at point J. So J is the final point. In this case, from this point to this point, it is getting down to a velocity of 0, which is the final velocity. It is going to be at what? At 0. So they are saying in within this period when we are at point H, from that point J to H, which is 250 meters from H. All right, sorry, this is our point J in this case. This is our H and this is our J. So the point J from H, they are saying there is a distance of 250 meters. We are given the displacement or the distance of 250 meters. Remember, displacement, the distance, that is the area under the graph. You are given that. This is of the last section from H to J. That is of the last section, this one. From H, if we're starting from this point J to H, not to say it is of this point of here, no. Just this section here, that is where we are given this displacement. It is only for this section. All right. So in this case, this is just our diagram that we are trying to analyze what is happening in terms of the information that you're given. With this diagram, if you understand it, it's going to be easier even to answer these questions, because there you just have to direct the displacement from F to G. So the displacement from F to G, if you are using the diagram, you can use the area under the graph. So there are two ways in actual sense that you can use to calculate this displacement. So you can use the area under the graph, which is from F to G, this one, this first section. So the area there is the area of a triangle, which is simply half base times perpendicular height, half times the base from this point, F, which is 0 to 30, that is 30, times the height, which corresponds with 90 there. So in this case, you are going to obtain 1,350. So this is 1,350 meters. That is the displacement. Or you can use the first information here that you are given to calculate this displacement, because they were given the U, the A, and the T. So remember that S is equal to UT plus half AT squared from our formulas of linear motion. That is, in this case, you can use this. That's 0 times the time, which is 30, plus half of the acceleration, which is 3 times the time, which is 30 squared. So this is the best formula that you can actually work with. So you're going to obtain the same answer there. That's another way that you can even have it. If you have it from the diagram, just the area. Just the area. So this, we have got the area from F to G. That is from F to G. All right. Then another part we are given the displacement from G to H. So from G to H, if you are to consider, we are now under this section here. So using our diagram, this is simply the area. So we've already calculated all those velocity. Remember, you've calculated this 90 and so on. So from that information, you can calculate your given displacement from G to H. So what shape are you having from G to H? That's a rectangle. So meaning to say we are going to consider the area of a rectangle, which is length times breadth or length times width. So the length, we are considering this side, which is 120, the difference between here 30 and 150, that's 120. That 120 that we calculated, remember? So that's 120 times the width, which is this side, which corresponds to 90. We already calculated this. Unless you have not calculated this, you have to calculate. Remember, we calculated this from that velocity concept. So that was going to give you the displacement from G to H, and that was 10,800 meters. All right. Then from there, we are now given 1.23, the time taken for the journey, meaning to say we are considering the time for the whole journey. Okay. We have got the displacement of this part, the displacement of this part, and the displacement of the last section, that one that was already given of 250 meters. From displacement, guys, we can calculate this time. All right, I want you to see something here. We can calculate this time. So that's 1.23. Remember, I want to calculate the time. So I'm saying from this total displacement, if you are to combine everything under this graph, this first part that we calculated, this one and this one, we combine everything. That is our displacement. So the first part, our displacement was 1,350. Second part, it was 10,800. The last part is the one that you're already given, the 250, that one that you were told before. So that is 250. So adding this, you're obtaining the total displacement, which was going to be 12,400 meters. Okay. So I want you to understand that this total displacement, remember, it can be calculated from the area under the graph. And of this area under the graph, if you consider from the point 0 here up to the last point, up to the last section here, up to the last section at the last point here, the value there is going to be T, which is the total time. So we can use this trapezium concept, the area of a trapezium. Remember, because that is the whole shape that you're given there. So this displacement that we are seeing here, it was taken from the area of a trapezium, half sum of parallel sides times the perpendicular height. So we have got the total displacement, 12,400 is equal to half of the sum of the sides which are parallel on this parallelogram that you are given. That is from 0 to the last point t, from 0 to t, that is t. So there we have got our time, the one that you want to calculate. So that is t, plus the other side, that is parallel from G to H, this one. So if you see, this is the resulting part from 30 to 150. So that is a difference of 120. So that side is 120 times the height between the parallel sides. This height is the one between these sides which are parallel. And that is the 90 meters that we are seeing there. So meaning to say, we have formed an equation with t. So you can calculate your time, which is the one that you're asked there. There are so many ways that you can actually use, but from this, you can also take it as an advantage because you've got the total displacement. So what are you going to have? Half of 90, that is 45. You can divide by the 45, by the 45, both sides. So this cancels. That means you are going to obtain 275,555 like that, which is equal to t plus 20. So you want to calculate the value of t, you can transpose the 20 that side, that will be a minus. So you're going to obtain 155,555 seconds, which is equal to t. So that was our time in this case, which is the total time. So with this one, we are calculating the exact total time at the end. That is our time that we are given there for the whole journey, which is that t. So like I said, guys, there are so many ways that you can actually use to calculate. Just make sure that of the way that you are using, you're obtaining the same value. If you're having the same value, then that's it. All right, let us consider 1.3. A flywheel is given that it turns 50 revolutions per minute. That is the speed, and the radius of the flywheel is 150 millimeters. All right, calculate the angular displacement theta of the flywheel in 10 seconds. All right, they were given the speed in revolutions per minute. That is 50 revs per minute, and also the radius of this fly, 150 millimeters. If we divide by 1,000, that will be 0.15. And the time, which is 10 seconds, and you're asked to calculate theta, which is the angular displacement. All right, we do understand that from this speed that we are given, we can calculate the angular velocity from there, the angular velocity, which is given as 2 pi n, provided that this n here is n revs per second, giving us this in rad per second. From the omega that we are seeing, also omega is equal to theta over t, meaning to say displacement over time. So from this, theta is equal to omega times time, which is measured in rad. Remember, omega here is rad per second times the time in second. This will cancel. You obtain your theta in what? In radians. So in this case, we do not have any part that we are going to use this radius, because this radius is used when maybe you're given the linear velocity, where you're given the meters per second, you want to convert to rad per second. That is where the radius is used. So in this case, it was just to substitute everything that you are given. So you can even calculate your omega if you want. The first part in this case from our omega, which is 2 pi n. You can calculate that omega if you want. Omega is equal to 2 pi n, that is 2 pi times n, which is 50 over 60. Remember, like I said, this must be revs per second to obtain this in radians per second. That was 5,236 rad per second. So with this now, we can calculate our theta, where theta is going to be 5,236 0.36 times the time in seconds, which is our time there, that is 10. So our theta was going to be 52.36 in radians. So this is direct in radians. If you were given the velocity in meters per second, they were going to use we're going to need that radius that we are given there. But in this case, guys, I don't even see where we are using that radius from the formulas that we have of linear and that of angular motion. That is what we understand. All right. Then we are given on the part of moments, give the difference between the concentrated load and the uniformly distributed load. So remember, the concentrated load, this one acts at a single point of a beam. Okay, so this one, it acts at a single point of a beam. This is what you have. Then the uniformly distributed is spread evenly. This one is spread evenly. All right, that is spread evenly over a certain length. Over a certain length of a beam. Or it can be of the whole beam. So it's considered like, is it the whole of or just a certain section? Then there we are given, all right, I just want to check if I'm going to use this section. Lucky enough, we do not have any other questions down there. Then we are given 2.2. From this part that we have 2.21, calculate the magnitude of the supports by taking moments about each support and test your answers using Newton's third law. The sum of forces up is equal forces down. So let's consider what we have on our diagram. Remember, this is all about analyzing the way that you understand. There is a distributed load that we are given 5 kilonewton per meter over 3 meters. So this simply means if I multiply this, I want us to properly see our diagram here. All right. So if I do multiply this 5 times this 3, that is 15. Okay. 5 times 3, that is going to be 15 kilonewton. So remember, this is kilonewton per meter, but it is separated between 3 meters. And so if you divide 3 divided by 2, it's going to be 1.5 meters between. So 1.5 is more than this one. So as you are to just sketch, make sure that your line is above, it's on this side, because 1 is on this part and 1 is less than 1.5. We need 1.5. It's more than 1, so it can be somewhere there. It can be just somewhere here, guys. This is just a sketch. So you gonna present with a point load like this. So this is, remember we said 5 times 3. Now we've got 15 kilonewton. So this is 15 kilonewton. All right, taken between 1.5, so it's just gonna be 1.5 here, meters, and also between these 2 points, 1.5 meters. So meaning to say, there is a difference of 0.5 between these points to be, between here. There's a difference of 0.5. 1.5 minus this one, that will be 0.5 there. There's a difference of 0.5, okay? Then let's do the same thing here. This way is easier because, guys, to say you consider what is on this side and what is on this side, you're going to work with a lot of things there. If you work with this, you've got 1. We work it as a 1 support like this. The same thing, 3 kilonewton separated between these 3 plus 2, which is 5. So that's 3 times 5, which is going to be 15 kilonewton again. But if you divide 5 and 2, this 5 here divided by 2, that's going to be 2.5. So it's going to be separated between 2.5 meters. That's 2.5 meters is greater than 2. So it's going to be somewhere there. Just indicate somewhere greater than 2, just bigger than 2. So we're going to have a support. I mean, a point load, not a support, guys. A point load like this, 15 kilonewton. So it's now 15 kilonewton. This one, don't use it because already you used it here, same as here. So you work with 15, separated between 2,5. So it's gonna be 2,5, also 2,5. So these are the new adjustments that you can make. And between here, 3 minus 2,5, because here it's 2,5. So 3 minus 2,5 means there's a difference of 0,5 there. So there's a difference of 0,5 in between, just like here, there's a difference of 0,5 in between. All right. So once your diagram is like this, it is easier now to consider our moments. All right, so let's consider the first part. I'm going to consider my moments about B, the first support, which is B. All right, so that's 2.21. So taking moments about B. Okay, so remember, sum of anti-clockwise moment is equal to sum of the clockwise moments. So if we consider about B, remember the clock, the way that the clock moves. This is your clockwise. So consider your clockwise, all right? Then anti-clockwise, the opposite, that is your anti-clockwise. Okay, so let's figure out what is happening to those forces going to be. The F, which is our support, as it is going to be, check. This is your F. As it goes to B, it's going to be like this. That is anti-clockwise. So meaning to say F is in the anti-clockwise. So we're going to have F times the distance, F back to B. So there's 3, 5, plus 5, plus 2 there, plus 3, I mean, which is 8, plus 1, which is 9. So that's F times 9. There's a difference of 9 there. All right, we are still in the anti-clockwise. We have taken this F. Let's see any other. So if you check these other forces, they are in the clockwise. They're moving like this. This is the clockwise. This is the clockwise. This is the clockwise. This is the clockwise. But if you consider this one on this side, it is moving this way. Remember our anti-clockwise way. So meaning to say, we also have 15 kilonewton. It's on the left side. So it's going to be 15 times between 15 and this B, there's a difference of 0,5. That's times 0,5. So these are the anti-clockwise, all the anti-clockwise that you're given. Now let's consider our clockwise. So on the clockwise, like I said, all these ones, they're on the clockwise. That is 10 back to 10 back to B, 10 times 1. Okay, plus 15 back to B. That is 15 times, it's going to be 4. This one, 3 plus 1, which is going to be 4. Then we consider 5 back to B. So we add, that is going to be 4 plus 2, which is 6. So that will be 5 times 6. And also the 15 kilonewton, it's moving also in the clockwise. Then the difference there is, remember, we are at 6 right now, plus this 3, which is going to be 9. So that's 15 times, oh, sorry, not 3, but it's going to be this one. 15 is going to be plus this 2,5. So it's this 6 plus 2,5. 6 plus 2,5, which is 8,5. So it's going to be 15 times 8,5. Take note from this point. We are not considering that part. Remember, there's a difference of 0,5. So the 3 is no longer considered there. So this is what you could have done, guys. I do not know how you took it, but with this one, still we're going to have our same F. So that's 9F plus, if you multiply this, it was going to be 7,5 is equal to, add up your right-hand side. That is 227,5. Transpose the 7,5, it's going to be a negative. So 9F was going to be 220. Divide by 9, you obtain your F. So that's our F, which was going to be 24,444 kilonewton. All right, so there we just obtained our F, which is 24,444 kilonewton. With the same sense that we used, we are going to calculate now, taking our moments about F so that we can calculate B. Remember our question there, it is to take moments about each. So this time about F. We are on F this time. So still considering the sum of the anti-clockwise moments being equal to the sum of the clockwise moments. Let's consider what's happening here. All right, considering B, and if you were to see B is going this side to F. So remember, this is the clock way. So that is on the clockwise. And if you consider this F here, it is moving this side, which is, oh, sorry, we are considering, I want this one at F, it is going this side, which is anti-clockwise, all these ones, they are in the anti-clockwise, except for the B that we are seeing there, which is in the clockwise. So all these ones, they are in the anti-clockwise, all of these. So let's start from the one that is just at F, which is the 15. So 15 back to F here, that is 15 times 0,5. Remember, there's a difference there of 0,5. Okay, then 5 back to F. That is gonna be this 5. So that is 5 times back to F. Remember, there's a 0,5. Actually here, we just consider the whole of this here. It's already what? 3. It's already there on your diagram. So that's 5 times 3. Okay, then 15 back to F. Remember, this is 3 plus this 2. So it's gonna be 5. So that's 15 times 5. Okay, we still have another one, 10. We are at 5 plus this 3, which is now 8. So that's 10 times 8. So this one is going to be 10 times 8. Then the 15 kilonewton is also going in the same way. So that's 15. Remember, this is 8, and there's a difference here of from here, there's 8 plus this 1, or just say, since this is 8, then we add this 1,5. So 8 plus 1,5 is 9,5. So that's 15 times 9,5. So this is equal to what we are given on the clockwise. And as we analyzed, we saw that it's only B which is going in the clockwise back to F. So that is B times the distance there back to F, which is 9 meters. So that's it. We have got our moments in this case that we consider. So combine your left-hand side. In this case, you're going to obtain 320, which is equal to B times 9, that is 9B. All right, so that's it. You can obtain B from there. So B was going to give us 35,556 kilonewton. So that is how we could have calculated, depending with the way that you're going to present on your diagram. The way that you are going to present there is actually very, very important. That is our question. So it was actually 5 marks on this. Let us consider the other part, which is now 2.22. That was to draw the shear force diagram using a suitable scale. Show all the main values on the diagram. So in this case, I'm just going to show you the main values, because these values, guys, there is no suitable scale that you can use to mark this point like 24,444, like that. This is something that does not even exist. So no matter the way that you want, guys, there's nothing that I can do. I understand most of us will be asking, use a proper scale. Even if you choose 100, 200, 300, you can't present, you can't mark this. So it is just for you to indicate, like to show those main values on the diagram. That is what they want. This part of the scale here, even them, they can't even do this from the department. They can't even have a proper scale that they can use. It's impossible. You can't present these decimals that you're given there. So you just present the major values, the main values that you are seeing. All right, so the shear force diagram, like I said before, you take it from the original diagram. You take it back to the original diagram. You analyze back to the original diagram. Remember, we calculated our B. That was 35,556 kilonewton. Then we calculated our F before. All right, sorry, the other thing that we wanted there was to prove this, to test. Okay, no problem. Just gonna test here. Let's see. You see, I wanted to explain that part of our major question that we always ask, like, why is it like that? So it's because of that, guys. You can't present this properly. So on this one, we are also supposed to test here and test your answers using Newton's third law. So to test, we are going to use the sum of forces up. We understand that the sum of forces up should be equal to the sum of forces going down. So in this case, you add these two, B and F, which are your supports, the one going up. So that's 35,556 plus 24,444 like this. These ones going down, remember those ones that you were having, there was a 15 here. There was also a 15 here. Those are the ones that you use. So that is 15 plus this one is 10 plus there is 15. Then we've got a 5. All right, a 5. And this one, it was a 15, like that. So that is, you add, you combine everything. So these are the ones that you are given, and that was going to be 60 kilonewton. And this one was going to be also 60 kilonewton. So that was to test your answers. You just use your sum of forces going up equal to the sum of forces down. So like I said, considering our shear force diagram, you consider back to the original diagram, like as it is, as you are seeing the diagram right now, you analyze that from the original diagram that you're given. So this part of our scale, this and that, guys, it's going to be something else. But I'm just going to show you like how it was going to look like. Then you just make sure as you are drawing, you must just draw something that is neat. Present your diagrams in a neat way. Do not say as you cannot have a proper scale, therefore even your diagram is not neat. No, your diagram also is supposed to be neat in terms of the presentations. All right, so I'm just gonna have a horizontal line that we are going to refer our points from. So this is it. You analyze from the first point. So you're going to start at A. At A, it's initially, that's at 0 there. So at this point A, maybe you are having your scale that you are given 100 and so on going up. This is 100, 200. You just use any scale that you're going to choose, like to say these points, they lie in between the given points that you are having. Not to say it is something that is going to be accurate. This is what I'm trying to say. All right, let me just put something like this, because here you're not going to have anything accurate. So maybe you are presenting this as 0, 10, 20, 30, and so on and so on. Then minus 10, minus 20, minus 30, minus 40, and so on. So this is what you're going, just to make sure that the points are in within that part. So at A, you are directly at 0. So you analyze this is what is happening. From A to B, in within A and B, there is a distributed load. So every distributed load, remember, it is supposed to be going down like this. So how do you indicate that distributed load? It's going to be at A, which is 0, minus, because the distributed is going down. So it's going to be minus, you multiply 2 times 5. So that is 5 times 2. meaning to say we are going to obtain -10. So that is going to be marked at -10 according to your scale. We're going to have it direct at -10, then you join. So guys, if I keep on doing this, it's going to affect, because these softwares, they do not want all this. So I'm just going to join, but you're going to have something like this from 0 to 10. So this is at -10 kilonewton. All right. This is at B. We are A to B. Direct at point B, there's a support. Direct at B, there's a support. And the support, you're going straight up. So you add this support, 35, whatever that you're given there, at -10 where we are. So we are going to add what is our support, 35,556, like that. So if you add this, you are going to obtain 25,556, meaning to say the support is going up to 25, up straight up to 25. Maybe 25 is going to be approximately somewhere there. You mark your point there, which is 25,556 kilonewton. That's what happened at B. Then you move on from B to C. 1 meter, there is a distributed load of 5 kilonewton per meter for this 1 meter. So we're going to subtract 5 times 1 again, just like what we had here, 5 times 2. At this value, 25,556 minus, it's going to be 5 times 1 because it's distributed for 1 meter. So that was it. You subtract, you're going to get 25,556. So remember how the distributed is indicated. It's going to be slanting down to 20,55, maybe somewhere approximately somewhere there. So you're just going to join somewhere there approximately. So that's 20, all right, that was 556. So it's 20,556 kilonewton. So this has gone down just a little bit. All right, we move on from C. From this point, we are now at C, direct at point C, direct at C. There is a point just after the distributed, direct at that point. There's no movement like you're going to move a little bit. No, direct at that point, there's a distributed load. So you subtract that as it is at that point, -10, you're going down. So at this point, you're going to subtract -10. Okay, that will be 10,556. So remember, this is a point load. It's going down straight down, just like the supports, they go up straight. They are opposed by what? By point loads. They go down straight. So it's going to be down to 10,556. So 10,556 maybe approximately here. So it's going to be going down straight down, maybe approximately there. That's an approximate, guys. Like I said, this thing of our softwares, we can't have anything exact there. So it's gonna be maybe like this 10,556 kilonewton. That's where you are. Okay, let's analyze again from our diagram what is happening after this 10 kilonewton movement. We are seeing that in between there's a movement of 3 meters. Nothing is happening here for 3 meters, meaning to say we are still at the same value. So you can just draw a horizontal line to represent that there is a movement that is not affected for 3 meters up to this point, D. At D, a point load 15, meaning to say we are going down again, just like the previous case. From where we are, remember, we were at what? 10, this value, 10,556. We subtract 15. So that was going to be -4,444, like that. So this is what you're going to have. And remember, this is a point load. It goes down straight to -4, maybe it's going to be approximately like this, just before the -10, just somewhere, maybe somewhere there. And it's supposed to be a straight line. Okay, so it's gonna be -4,444, like that, kilonewton. Okay, That is at what? At D. From D to E, what is happening? From D to E, again, there's a movement there. There's a gap between these 2 points, 2 meters. So you just move straight horizontal, meaning to say we are at minus at minus 4,444, whatever value that you are having. Just move to a certain value there. Okay. Now, after this movement, there's a point load, 5 kilonewton. Point load, remember how you work a point load, you subtract. So it's minus 4,44 where we are here, then minus 5. So it was going to be minus 9,444 like that. So that is a negative 9 that we are given. All right, sorry for that. So that's a negative 9. And this, remember, it was taken from a point load. So we're just taking it straight down. And negative 9 is below negative 10. Sorry for that. So it means we just have a small point there. Okay, just a small. Okay, why is it not allowing me, guys? Like this, just a small value there. Negative 9,444, like that. Okay, then this is what is happening here. At this point, remember we are at negative 9, whatever that we are there. There is distributed load between the point E and F, between this point for 3 meters of 3 kilonewton. So meaning to say at this value where we are at negative 9,444, we are going to subtract a distributed load. Remember, is 3 for how many meters? For 3 meters. So that was going to give you, in this case, negative 18,444, like that. So remember, that's a distributed load. How you present it this way, like I said before. So that will be our distributed load up to negative 18. So negative 18, just approximately below negative 20, somewhere there, like this. That's a distributed load. Negative 18,444 kilonewton. Okay. Then here we have got at F, direct at F. F is a support. There's a support here of 24,44. So we're going to add. Remember the support, it adds because it's going up. So at this value, if you add 24,444 like that, you were going to obtain 6 kilonewton, which is a positive, and it's going up. So 6 just below 10. So you're going to have it straight up. Remember, it was a support. So maybe roughly somewhere there. That is at 6 kilonewton. Going to be a support. Then from this part, we are given the last section from F to G. It's distributed. The same 3 kilonewton for 2 meters this time. So meaning to say at this 6, we are going to remove our distributed load. 6 minus 3 times 2. So that was going to be a 0 kilonewton. So if you combine up to the last stage and you do not obtain a 0 like that, that means everything is actually wrong, because you must start at you must have a closed shape like this, a closed figure on your shear force diagram. So that is what you are going to have at the end. So these are the major points that you are supposed to indicate on your shear force diagram. That is the major values that are presented there. So make sure that you do understand the information that you are given, like the way that you're given, your diagram, everything. So that was our question 2. Let's consider question number 3. On question number 3, first part was to define a parallelogram of forces. Remember, this we are considering if two forces acting at a point are represented in magnitude and direction by two sides of a parallelogram. So they are going to be presented by two sides of a parallelogram meeting at a point, and their resultant taken as the diagonal that is presented. So that is our parallelogram of what? Of forces. This one we are used to, guys. We talked about this a lot of times. Let's consider question number 3.2. We are given to copy this part and calculate the magnitude and direction of the resultant force of systems, force of the systems that are given. So let's see what exactly we are having. This is what you are going to consider as your sketch. Analyze this diagram, like I said before. If you can consider properly, they are simply giving us the straight line, which is the east and the west, and also here the north and the south. This is what you're simply given there. So if you consider properly, you see that the 300 Newton, this one, the 300 Newton, it is taken, look where the arrow is. Remember I said the forces, if you do not want to have confusion, take your forces from the point where they do meet like this. Take these forces from, the arrow must be pointing away from, must be from this point, not to be pointing inside like this. It's going to be difficult for you to understand. So what do? You just continue with this. You see the 300, this one, it's pointing inwards. So you just continue with it straight. So you're going to have the 300 here straight this side. That is where it is going. So meaning say you are no longer considering this 300 this side. You are considering it this side. This is where you have your 300 Newton. Which other force is pointing into this? Also this 150, if you see the arrow here is pointing inside. So you have to take it to the other. Just continue with it. Do not make any special constructions there. This as it is, you just continue with it. Must go down as it is. Just continue with a straight line. It's a straight line. Just have a straight line as it is, like this, going down. So meaning you say you are no longer considering this 150. You are considering this one, which is down here. This is the one that you're now having on your diagram. So what is the angle in between? If you consider this angle here, that, remember, this is a straight line here. So this angle and this angle, they are equal, vertically opposite angles. This is now your mathematics. Go back to your mathematics concept, the geometry concept. This angle here and this angle are called vertically opposite angles. They are equal. So meaning you say if this is 65, this is also 65. Remember, we want the angle from the force to the what? To the horizontal. So that is the 65 degrees. Okay. This one of 600, there's no adjustment. It's already facing out. It's already out. So the angle is also there. The angle is also given the 20 degrees and it's from the between the force and the horizontal. So this one is fine. So this is no longer there. This is no longer part of our diagram. Our diagram is now considered with this 250, which there's nothing that changed here. The 600, nothing changed. And this one, which changed. This is your new diagram. With this diagram, we can calculate our components now, the horizontal, vertical. All right. So the horizontal component, remember, you're considering the cos. There is no way that this can be a horizontal. This is a straight vertical pole. There's no way this can be a horizontal. Yes, if you want, you can write 250 cos 90 if you want, because there's an angle between here of 90 degrees. But there's no way this is a vertical pole. It can't be horizontal. So you obtain a 0 there. There's nothing. So the horizontal that we have, there's a 300, which is on the negative side. So that's negative 300. The 600 can be written as a horizontal if it is multiplied to the cos, but in the negative region, as we can see. So that's negative 600. The cos of what? 600 is the one that is at 20 degrees. Okay. The 150, again, it's on the negative side. So that will be negative 150. The cos of the angle, which is 65 degrees. With this, you can obtain your horizontal component. You can obtain what is on the horizontal component with this. So that was going to be negative 927.208 Newton. So that is our horizontal component. The vertical component, in the same sense, we are going to, this time, the 250 that we said before. It's on the positive, and this is a straight vertical pole. So there's no way we're just going to take it as it is. 250. The 300, is it vertical, these guys? That's a straight. That's why even here, I never wrote like cos this. It's a straight horizontal line. It's in the, that's a straight horizontal line this way, the east. Just like when we are on the south and the north, those are straight vertical poles. So we just take them as they are. There's no need for you to write the sign of 90. Yes, you can write a sign 90 in this case. There's no effect at all, or just 250. The 300 cannot. So we're going to take the 600. It's below. Remember, this is below. Everything below, considering being vertical below, carries a negative. So 600 is going to carry a negative. Negative 600, the sign, vertical carries the sign. That is sine 20 degrees. The 150 in the negative also, negative 150, the sign of what? 65 degrees. 150, the sign of 65 degrees. So these are our vertical components. That was going to give us 91, that was negative 91,158 Newton. So in order for us to have the resultant and so on, we can just analyze this on our diagram. Where is it that the horizontal is negative? For this horizontal to be negative, if we are to consider this, we are talking about the west side in that case. And for this vertical to be negative, we are considering down, which is the south side. So that is on our diagram, we are going to have something like this where both are negative. So it's just going to be like this. Remember, we just want to consider the west and the south. So it's going to be something of this nature in between. So this is the angle that you're going to take in between the west going to the south. This is your horizontal here. That's negative 927,208 Newton. This is your vertical component, negative 91,158 Newton. So that's it, guys. You can calculate the resultant and the theta. So the R there from our Pythagoras theorem, that is the square root of h squared plus v squared horizontal, which is gonna be something like this. All right, so we're gonna consider this as the square root of negative 927,208 squared plus that's negative 91,158 squared. So that will be our resultant. So in this case, we're going to obtain 931,678 Newton. That was going to be your answer, and your theta can be calculated from arctan. Remember, guys, opposite and the adjacent concept. So that's opposite over adjacent. Negative 91,158, of which you can just ignore that negative that you are given there, or you can just put it, there's no problem. That was going to give us the angle of 5,615 degrees. From the west going to the south, the direction there. So meaning to say, therefore, our R being 931,678 Newton at west going to the south. So that is west 5,615 degrees to the south. Or you can consider this as from the south to the west, but you have to calculate this angle. If you consider alpha, that will be 90 degrees minus the theta, the 5,615. If you want to indicate it from the south going to the what? To the west. It can be your solution like that. So the presentation thereafter is in your hands, like I said before. How are you going to present your answer thereafter? So that was part of our solution on this question 3 that you're given. Then 3.3, we have got a condition here that if two pulleys are used on a system of forces shown below are frictionless. So these frictionless pulleys, calculate the values of x, y to keep this system of forces in equilibrium. For this to be in equilibrium, remember you're going to consider in terms of your components. Remember the definition of being in equilibrium. The horizontal components must be equal to 0, the sum. The vertical must be equal to 0. So if the sum of the horizontal components is equal to 0, let's consider the horizontal components. Guys, that's the x at this point. This is just the 50 kilograms that is going to affect here. So meaning to say we can consider that. Force times distance, if you consider that, even with the mass, because the g, which is the gravitational acceleration, is the same. So wherever there is a weight, you're going to consider mg, which is the same throughout. So instead of using that gravitational acceleration, you can use the mass as it is direct. So meaning to say, what is the horizontal component? If given x and there's an angle of 20 degrees, remember horizontal component carries the cos. And this is on the left side. It is on the negative side. What are we having there? So meaning to say, if we are to consider that combining this, we are going to have this as a negative, or we can consider the other part, the sum, the combination of both. Meaning to say, we are going to have x, the cos of what? The cos of 20 degrees. So considering what we are given on the other hand, because this must be equal to on the other hand also. Or you consider this as the sum. If you consider the sum, that will be a negative. The way that this is in your hands. So if you consider this as a negative, then you must add this one, which is, okay, the y there is at this point, guys. Look where the forces are taken from. So this cannot be horizontal. Remember, I talked about this before. That cannot be horizontal in the same sense as what we saw here. We never talked about the 250 on the horizontal. I never indicated that. It's not there. That's a straight vertical that we are having there. So you're not going to talk about that. So you add the 50 cos of what? Cos of 50. This must be equal to 0. It's an equation. So meaning to say, we are simply saying 50 cos of 50 degrees is equal to, if we take this to the other side, it becomes a positive. That's x cos of 20 degrees. So you can divide by the cos of 20 degrees both sides. So since the gravitational acceleration, like I said, it can be part of your formula, but there's no need for that. There's no need, because it's the same. It's the same gravitational acceleration. So that was going to be 34,202 kilograms. That is what you have. From the horizontal component, the sum, they're in equilibrium. Or you can consider they're equal. The left-hand side is equal to the right-hand side. It's up to you. So in the same sense, also the sum of the vertical components must be equal to 0. Everything in the vertical. So if you consider this to be a vertical, it means that's x, the sine of 10. And it's on top. So that's a positive. So you've got x sine of 20 degrees in this case. Remember what I talked about this y before, that it's a straight vertical component that we are given going down. That's a negative. So that's negative y in this case. The 50 is at this point here, it's on top. Remember, this is it, guys. So this is on top here. So meaning you say you've got 50, sine 50 as a vertical component. You're going to add this. So that's plus 50, the sine of 50 in this case. So that is equal to 0. You want to calculate the value of y, so you can transpose y. This side is going to be a positive. So on the left-hand side, we are left with x sine 20, which is our x. Remember, that's 34,202 that we calculated. That's the sine of 20 degrees plus 50, the sine of 50 degrees. So this will be equivalent to the y. We've transposed this to the other side. It becomes a positive. So add up this, you're obtaining the value of y direct. So it was going to be 49,999 and so on. So that is actually 50 kilograms. So that is how you could have calculated this. You can consider the condition that you are dealing or you are working with the equilibrium concept. So meaning to say the sum of forces, for it to be in an equilibrium, they must add up to 0, considering the horizontal components. You work with the horizontal components on their own. Considering the vertical components, you work with the vertical components on their own. So you must be able to understand each and every concept that you are given, guys. It's the statement that you are given that you are working with. The information is the one that you're working with. What is it that you are given from there? All right, so that was our question. Question number 4, we are here asked to state 4 advantages of friction. Friction can be an advantage in engineering, okay, since it brings movement to stand still. So you know that it brings movement to stand still. That is the purpose of friction. Also, this friction transmits movement by means of belt. So it also transmits movement by means of belts. So this is by means of belts. Okay, we also consider removes material. Removes material. So according to our syllabus, this is important for you to have. It also prevents slip between. It prevents slip between 2 contact surfaces, All right, so like I said, according to your syllabus, it's best that you do understand these ones. And there we are given a block with a mass of 0.5 tons. So given the mass of the block, that is 0.5 tons. Remember, a ton is equivalent to 1,000 kilograms. So multiply by 1,000, that is 500 kilograms in this case. It is inclined. It rests on an inclined plane which is at an angle of 35 degrees to the horizontal. Okay, let's just have this, and there's a friction force of 0.21 kilonewton. So that's it. Just multiply by 1,000. That will be 210 Newton, or you can just leave as it is. All right, so let's just try to have a sketch of what is happening here. So just consider your sketch, guys. Do not worry about much. That's 4.2. So it's on an incline. So that's definitely something like this, which is at 35 degrees. So we are given, this is of 0.5 ton, which is 500 kilogram. So that's going to be 500 kilogram. There is a friction there, a frictional force. It's opposing. So the frictional force, as it goes up like this, the friction will be opposing the other way. So meaning to say, we're going to have our frictional force of 210 Newton. Also, remember, we're going to talk of the parallel component in this case. We're going to talk of the perpendicular component in this case. We're going to talk of the weight, which is equal to mg. Guys, there are a lot of things that you're going to need about there. So that is it. Let us just see what our question is about. The question was the component. Determine the component of weight of the block parallel to the plane. The one that is parallel to the plane, that is our F parallel. Okay, so that's it, 4.21. So F parallel, remember, it is given as mg sine of theta from W sine theta, which is the weight. That says, since there we have got the mass, we're going to use the mass 500 times the gravitational acceleration, the sine of 35 degrees. So that's it. You're going to have 2,810.525 Newton. And that is it. You're going to convert to kilonewton if you want. The component weight perpendicular to the plane. The one perpendicular, that's our F perpendicular there, which carries the cos. So that's 4.22 F perpendicular, or FC. That is going to be W sine theta. So it's mg cos theta. I mean, it was supposed to be cos. So it's going to be mg cos theta. That is the mass of 500, the gravitational acceleration, 9.8 times the cosine of the angle, that is cos 35 degrees. So the product there was going to give us our perpendicular component, which is FC, or we can write it like this. That is 4,013,845 Newton. So that's it. Let's check what we got here. On 4.23, now they need you to calculate the smallest force parallel to the plane required to pull the object upwards along the plane. All right, so this is going up. So that's our F up. So remember that F up, that's 4.23. F up is the sum of the frictional force and the parallel component. All right. So if you're using FS, guys, it's up to you. You can use FS here. You can use FC. It's up to you. Okay. So it's the sum of this. We've got the frictional because these two, remember, they are going the same way. So F up is the one that is going up there. So it's the sum of these two opposing your parallel component and your frictional force. So there we have got 210 plus the parallel component. Remember, we calculated this 2810,525. So that was going to be the sum of this, which is 3020,525 Newton. That's it. Let's see the other part of our question, which was now to calculate the coefficient of friction between the plane and the block. So remember the coefficient of friction, we were not given actually, but we can calculate this. That's 4.24. The coefficient of friction from the frictional force over the normal direction, but we can use the perpendicular component because of the angle that is affecting. You use your FC or your perpendicular force. So meaning to say our coefficient of friction was going to be the frictional force is already there, 210. The perpendicular is already there also. So it was just going to be a substitution. That is 4,013,845. Remember, we calculated this. That was going to give us 0.052 as the coefficient of friction. So for 12 marks, guys, that was enough friction. Okay, this is actually interesting to have something of that nature because we can see that in most cases, it can be that difficult, but in this case, it was something that you can consider as a direct question that you are having there. So make sure that you do work with your formulas and also the diagrams. You see that it's all also playing a. All right, so considering question number 5, we are given 5.1, that was to define the specific heat capacity of a substance. So we are also used to our definitions here. So this is simply, it can be defined as it is the quantity of energy. So this is the quantity of energy required, quantity of energy that is required to raise the temperature. So it's going to raise the temperature, to raise the temperature of a 1 kilogram of a substance, And this must be raised within or by 1 degree Celsius. Okay, so guys, we are used to our definitions there. 5.2. We are given state 3 factors that must be considered or that must be taken into consideration when a substance has to be cooled or heated. You have a substance that you're supposed to heat. Remember that the heat is equivalent to the mass times the specific heat capacity times the change in temperature. So there are 3 concepts there that you must consider, which is the mass of the substance that you are given, mass of the substance that you are to consider. Then you consider the specific heat capacity there. So you take it from your formula, all right? You consider the specific heat capacity, and you also consider the change in temperature. The change in temperature that you are given. So these are the 3 factors that you must put into consideration as long you are to work with the heat that is to be cooled or to be heated. So you are going to see that in this question 5.3, where now they want you to determine the final temperature, given that there are 6 aluminum bars of 0.9 kilograms. So given the total mass, you can obtain the total mass. There are 6. So we have got, let us just consider the information that we are given there. So there we are considering the aluminum. All right, there we are considering the aluminum bars. So the mass, there are 6. Each has got a mass of 0.9. So meaning say the mass was going to be 5.4 kilograms. And we consider heated to 200 degrees Celsius, but immediately they are immersed in water, in 30 liters of water. So meaning say this is the temperature of aluminum when it was heated to a certain temperature. That was 200 degrees Celsius. So we also consider the part of water when it was immersed in 30 liters. Volume of water, a liter is equivalent to 1 kilogram. So it gives us also the mass, that is 30 kilograms of water. So in that case, considering the water, we've got the mass of water, which is 30 kilograms. So it is heated. This mass of water has got a temperature of 25 degrees Celsius. This is the temperature of water. That water that we are given, it has a temperature of 25 degrees Celsius. And from there, we are given to calculate or to determine the final temperature of aluminum bars and water combined. So that's our T2, the final temperature of these two. What is it? So from your formula sheet or from the information that you're given, you are going to see that you're also given the specific heat capacity of this aluminum. So you've got the specific heat capacity of aluminum. You are given that one as 900 joules per kilogram degree Celsius. And also for water, you are given, so you're going to take their specific heat capacities from your information sheet. So that is also in joules per kilogram degree Celsius. You're given these values. So the question was to calculate T2. Remember that we do understand that the heat that is lost is equivalent to that is being gained. The aluminum was immersed in water, so it's going to lose its heat as the water increases its heat. So it is the aluminum in this case which lost. It is the water which gained the heat. Now, remember this temperature, 200, immersed in 25 degrees Celsius, guys. So it's going to increase its temperature. So the heat, the formula does not change. That is the mass, the specific heat capacity times the change in temperature. The mass, the specific heat capacity times the change in temperature, but the mass of what? Of aluminum, the specific heat capacity of aluminum, and this change in temperature is supposed to be what? That temperature of aluminum, which is the initial temperature that you're given. When you immerse in water, its temperature will reduce as this one of water will increase. So that's why we are saying it's T aluminum minus T2, because it's gonna increase. Yes, this one, it's an increased value when you compare it from water, but from aluminum, because you are cooling it. So it is the one with a bigger temperature. So it's T aluminum minus T2 is equal to the mass of water, the specific heat capacity of water. The change in temperature this time is going to be the final minus that temperature of water. So this is what you're given. So let's substitute the aluminum side, the mass, that's 5.4. The specific heat capacity of aluminum, like I said, you have this from your information sheet, times the change in temperature, the temperature of aluminum, 200 minus T2 is equal to the mass on this side, that is 30, the specific heat capacity, 4187, times the difference between the T2 that you're supposed to calculate minus the temperature of water, which is 25. That's an equation that you have formed. From this equation, solve for T2, solve for this temperature. Okay, you can multiply these two. That was going to be 4,860 into 200 minus T2 is equal to multiply these two. That was going to be 125,610 into T2 minus 25. So guys, just get rid of those values. I know they are stressing values, but just get rid of them. Multiply, distribute inside. That was going to be 97200 like this. Minus, you multiply these two, that will be 4860 T2. Okay. Let's multiply this times T2. That is going to be 125,610 T2. Then we multiply it to minus 25. That will be minus 3140,250 like that. So let's combine the terms with T to one side. I'm going to transpose. I'm just going to take this number here. It becomes a positive. That will be, you add. So you get 141,2250. You add these two guys, this one and this one. It's a positive there. You take this negative, this side, it becomes a positive. It was a negative. So this side, it will be a positive. So you add these two values. It's now a positive. It will be 130,470 T2. So to obtain T2, definitely you divide by this number that is multiplying. All right, so you divide it there. That's going to be our T2. So in this case, our T2 was going to be 31,519 degrees Celsius. That's the final temperature when for both aluminum and water combined together. Guys, these typical questions, I have talked about this, I don't know how many times. Guys, I just hope for those who are following our videos, these things are now just like go through questions. All right, anyways, let's see. 5.4, a lead rectangular block, a lead. We are working with lead there. So that's a rectangular block that you are given at, which is the initial temperature of 27 degrees Celsius. The dimensions, so we are given the dimensions 350 millimeters by 450 millimeters, is heated and the temperature increases by 75. The change into it's an increase there, which is an increase. 5.41, determine the final temperature in Kelvin, the final after the increase. Guys, if there is an increase, therefore the final temperature, which is our T2, it is simply T1 plus that change in temperature. Remember, that's an increase. So T1 was 27 plus the change in temperature, which was 75. So this will give us 102 degrees Celsius, but they are saying in Kelvins. So how do you convert to Kelvin? Add 273. So our T2 in Kelvin, that will be 102 plus 273. That is to convert to Kelvin. So it's going to be 375 Kelvin. Okay, so that was straightforward question. Exactly. That is what you needed. Let's see. Another part. Calculate the area of the plate at the final temperature, at the final 3 marks, because we have got the area at this original temperature T1. So what about at the final temperature? We know that at the final temperature, the change in area is equal to the original area that you were given times 2 times the linear coefficient of expansion times the change in temperature, which is simply represents beta. So this is the change in temperature, but the question needs us to calculate the final, whereby the final area will be the sum of the two, the original area that we had, and that change in area. So the original area is simply the length times width that you are given. If you work with millimeters, it means you're going to obtain your answer in square millimeters. Use that, it's fine. You can convert to meters, that's up to you. You can use the millimeters as they are. So the original area is a rectangle, length times width. You're already given the expression for area 350 times 450. That's our area of this rectangle. Times 2 times alpha, which is the linear coefficient of expansion of this lead. From your formula sheet, you are given the linear coefficient of expansion of lead, which is 54 times 10 to the exponent of -6. So this value, you have it, times the change in temperature. Already you are given, guys, the change in temperature, that's 75. So there's no need for you to calculate this again from T2 minus T1. So there you are calculating the change in area. Since I was using the millimeters, it means my change in area is going to be in square millimeters. So that was gonna be something like this, in square millimeters. And therefore, the final area from our formula, the final area is the original area that we calculated, which is the 350 times 450. This is our original area plus the change in area, which we calculated of 1275,75. This in square millimeters, this also in square millimeters gives us our final area in square millimeters if you have to work it like that. So that was going to be 775,75 square millimeters. If you're using square millimeters, if you're using meters, it's fine. Convert to meters, it's up to you. That was gonna be like that. 3 marks, guys. Okay, let's consider 5.5. Steam is generated in a boiler at a pressure. So we are given the pressure of the steam at 1000 kilopascals. For 2 kilograms of steam, 5.51, determine the saturation temperature. So the saturation temperature is simply the temperature at this pressure. So from your information, from your steam table, this one, you use the steam table. You must be given the steam table. So I want you to see on your steam table. If you consider your steam table, you're going to see this is your pressure. This is your TS, your saturation temperature. So you need the pressure to be 1000. So we need our pressure to be 1000. So let's go down 1000 here. So if you are to consider when our pressure is at 1000 here, this is the corresponding value of our saturation temperature. Remember, this is the saturation temperature. So that is going to be 179.9 degrees Celsius. Remember, your saturation temperature is measured in degrees Celsius. If you consider here on top, our saturation temperature is in degrees Celsius. So meaning to say your pressure in kilopascal, saturation temperature in what? In degrees Celsius. So in this case, you were going to have your answer as degrees Celsius, all right? So that is, that was going to be your saturation temperature in this case. So it was going to be 179.9 degrees Celsius, okay? It has no effect whether the steam is 1 kilogram, it's 2 kilograms, does not affect. It was going to affect this. The enthalpy of dry saturated steam. The enthalpy of dry saturated steam, we understand this is our Hg. So what is our Hg at this same pressure of 1000 kilopascal? Just like what we had on our temperature, we are going to take this time Hg, which is given at this point, this our Hg, which is in kilojoules per kilogram. So you need the pressure to be in kilopascal and straight to that Hg. So let's go down and see. All right, that was gonna be this one. So this is the column of Hg 1, 2, 3, the third one. So we're gonna consider the third column. from the end, the third column from the end, the third column from the end. That's what I'm trying to say. So at 1000 straight, we were going to see that is the third column, this one. So this is 2777 kilojoules per kilogram. Remember, your answer is in kilojoules per kilogram. So you needed your steam table. That's per kilogram. This one is measured per kilogram. 277 like that, kilojoules per kilogram. But you are given for how many kgs? For 2 kilograms. So you multiply by the mass, 2 kilograms. So it follows that kilojoules per kilogram times a kilogram cancels like this. You obtain the kilojoules. So your answer by multiplying by this mass, it is no longer in kilojoules per kilogram. It is now in kilojoules. So it was going to be 5,554 kilojoules, like I said. So that was it to determine the enthalpy of the dry saturated steam. So you need the steam table to answer that. All right, then you're given question number 6.1 to state Pascal's law. So remember that the Pascal's law is simply taken that it states that the pressure change, that a pressure change at any point in a confined fluid is transmitted equally in all directions throughout the fluid. So it's going to be transmitted equally in all directions. 6.2, you're given a single acting pump. All right, that's a single acting pump that you are given there. So just consider, guys, your single acting pump just gonna be something like this. All right, so there we are given on this pump. It has got the plunger diameter of 150 millimeters. Just divide by 1000. We've got the diameter. The stroke length 25 centimeters. So we've got the diameter. 0.15 meters. Then the stroke length, if we divide by 100, it's going to be 0.25 meters. This is, so it is delivering water into a tank 2000 centimeters vertically above the ground. So again, divide by 100 is going to be 20 meters. So the height of the tank, so this will deliver in a tank. And this tank is the one that has got a height of 20 meters. Okay. So our question is calculate 6.21, the delivery pressure. What is going to be the delivery pressure? So the delivery pressure, we can consider where it is. We are delivering water in the tank. So that is from the tank. So meaning to say our pressure is going to be the 6.21. Remember that pressure is equal to the density, the gravitational acceleration times the height. The density of water, which is from your information sheet, that is 1000 times the gravitational acceleration of 9.8 times the height of the tank. That was going to be our pressure in this case, which is 196,000 pascals. You can also write in kilopascals if you want. That is in your hands. The work done per delivery stroke of the plunger, which is 3 marks for that. Okay, so remember that the work done can be calculated from the pressure and the volume, which we can have from that, which is 6.22. The work done, remember that it's pressure times the volume. So from this, we can consider the volume that is from our piston there. That is the volume can be calculated area pi d squared over 4 times the stroke length. So there we've got the volume. So meaning to say, in this case, it was going to be the pressure 196,000 times the volume pi d squared, which is our area, the diameter 0.15 squared over 4, sorry, times the stroke length, which is 0.25. So with this, guys, you have got your work done. It's nothing that is much special there. So that is gonna be 865.901 joules. So we have got the work done per stroke. Then the mass of water in liters. Remember, water, 1 liter is 1 kilogram, but we do not have anything about mass. So what is it that we can use? We can think of the volume, because the volume can be considered to say a cubic meter is equal to 1,000 liters. So we can consider volume. We are given after 15 strokes, the number of pumping strokes is 15. So remember that volume can be calculated from that. So you can consider volume there. It was going to be easier that way, 6.23. Remember that the volume is simply from this formula that we had, pi d squared over 4 times h times the number of pumping strokes this time. So meaning to say that was going to be the part of the area, this one that we had, it was going to repeat. You see these guys of not calculating our values. But anyways, guys, you have got your values, just substitute. Number of pumping strokes we are given this time after 15 pumping strokes. So that was going to give us the volume, which is 0.06626, whatever value that is on your calculator, it is in cubic meters. But like I said, a cubic meter is 1,000 liter. So to convert to liters, the answer on your calculator, straight multiply it by 1,000. That's you're converting your volume to liters. So it was going to be 66,268 to 3 decimal places in liters. You're converting your answer now to liters. Yes, they are saying mass in liters. Mass is that in kgs, but it can be volume. That is the volume there. 6.3, a force of 480 exerted on a hydraulic press. A force exerted on a hydraulic press. That is the that is the plunger side, sorry. So meaning to say we are given the information happening on the plunger side. Remember, just gonna have our sketch here. So let's just have our ram and the plunger. So there's no need for you to have the diagram, guys. So on the ram, we're gonna have the capital letter F, the D. Here we're gonna have the small letter F, the small letter D, just to represent what? The plunger. Okay, that's what I'm gonna do to indicate that, so that we do not have confusion. So we're given that there is a force of 100 exerted, the force that is exerted there on top, that is on the plunger. So we've got the plunger, force of 480 Newton. All right, then from there, we're given the diameter of the plunger is 35 centimeters and the stroke length 150 millimeters. So divide by 100, divide by 1,000. All right, so we've got the diameter. This is of the plunger. So I'm just going to use small letter D. That was going to be 0.35 meters. And the stroke length was going to be 0.15 in meters. Then also we are given the diameter of the ram, which is 900 millimeters. So on the ram, we just going to have the capital letter D. That will be 0.9 meters. Okay, if we divide by 1,000. So the question was to calculate 6.31 force exerted by the ram. So the force exerted by the ram, according to this, we've got the diameter, and we've got the force. Remember, there is that formula which connects the forces that we are given. This is 6.3, and this will be 6.31. So remember that the relationship force over d squared, considering the ram, is equal to F over d squared on the plunger. Or you can use the plunger to the ram, it's up to you. You can even use the diameters on top, it's up to you. So in this case, I can calculate this force on the ram, multiply by d squared both sides, multiply by d squared both sides. So this was gonna cancel. So meaning say the force on the ram was going to be this formula. This is the plunger, remember? So you're gonna consider the force on the plunger. Okay, the force on the plunger, which is 480, the diameter of the plunger, 0.35 squared. And this is the ram, which is the 0.9 squared. So that was going to be the force on the ram of 3,173,878 in newtons, just like that. So that's it. Then the distance moved by the ram per stroke of the plunger, and you're not given the number of strokes. You need the distance moved. So you're going to consider the volume concept. Remember from the volume concept, the 6.32. All right. So in this case, guys, we need the diameter. Let me just put it a little bit, guys. It's too much. Just like this, you're going to see 6.32. Remember from the volume concept, we know that the volume on the ram must be equal to that on the plunger, and that's pi d squared over 4 times h. Given the number of pumping strokes, we're going to use them, but we do not have that. This must be equal to the volume on the plunger, which is going to be pi d squared over 4 times h. So we need to calculate this h, which is on the ram, the distance moved by the ram. So what is it that you're going to do? We can see that the pi over 4, the pi over 4 are the same. They can cancel. So instead, we can minimize our formula. D squared h is equal to d squared h. I need this h, so I can divide by this d squared both sides, which is of the ram. So meaning to say the height moved by the ram is going to be the product of this, which is of the plunger. This is the plunger side. That is the diameter of the plunger, 0.35 squared times h, which is the stroke length of 0.15, everything over d squared from the ram side, that is 0.9 squared. So that was going to be h 0.023 to 3 decimal places. That's it. So guys, also how to manipulate your formulas is very, very important that you do also understand how to manipulate your formulas. Electricity on question number 7. What is meant by terminal voltage? So this is the potential difference across. So it is the potential difference. It is the potential difference. So you're going to consider the potential difference across the terminals, across the terminals of the battery. Across the terminals of the battery. That's it. So they were given 7.2. The circuit above is a battery with an EMF of 12 volts, which is what you're given. The circuit is resistors 6 and so on. And the current of 3 amps, these are the resistors, and the current through these resistors is I2. The current through these resistors is I2. So let's say this is I2 according to what we are given. Okay. So that is it. That is it. That is it. So the question is, from this diagram that we are seeing, calculate 7.21, the current through 2 ohm resistor. This is the 2 ohm resistor. So there they want us to calculate I2. That is, calculate I2. Remember, they say this is I2. Okay, what can we do? This combination is a parallel combination. And in a parallel, we do understand that the voltages are the same. In a parallel, the voltage is the same. VP is the same. And we can calculate that voltage because there is a current and a resistance here in parallel. Remember, current times resistance is voltage. So you can use the current of 3 amps times the resistance of 6. We've got the voltage of 18 volts. This is the voltage in a parallel combination affecting both here. So it's going to be 18 volts here. So having a voltage across, we can calculate the current because we do understand that current is voltage over resistance. So using the parallel voltage that you're given, and the resistance is the combination of these two. There are 2 resistors that you are given in that the current of 2 amps, the current of I2 affects these 2 resistors together. It is the same current flowing there. So that is going to be 1.8 amps. So that's our I2, 1.2 amps. The reading on the ammeter. So the ammeter, according to this, our Kirchhoff's law, this is the current entering. 3 amps and 2 amps are being taken from the supply. So meaning to say the supply is the sum of these 2. So that's 7.22. That is the total current from the ammeter. That is the total current, which is the sum of the 3 amps and the current I2 of 1.8 amps. So it's going to be 4.8 amps. Just like that. Okay, so there we are given ammeter current across. So you can use your Kirchhoff's laws. All right, so that was it there. Just like that. 7.23, we are given the value of the resistor marked R. The value of the resistor marked R. Let's go back to our diagram and see where this resistor is. So this is our resistor R here. What is it that we can use? Remember from the voltage drop concept, we have got a 12 volt here and we have got an 18 volt. So meaning to say there's a voltage drop across this resistor R. So we can calculate the voltage drop across the resistor R so that we can obtain the resistance. Remember, the current there is the same as the current flowing across the ammeter, which is the supply current of 4.8 amps. It is the same current flowing here of 4.8 amps. But what we do not have now is the voltage. So we can use the voltage drop. We can use the voltage drop concept. So that's 7.23. So the voltage across this resistor that we do not know is simply the difference, 18 volt minus 12, the voltage drop, which is going to be 6 volts. So there is a voltage drop here of 6 volts. Where a current of 4.8 amps, having current and voltage, we can calculate resistance. Remember, that's the voltage over current. So meaning to say our resistance R is going to be 6 over the current of 4.8. That's our resistance, just like that, 1.25 ohms. So guys, just make sure you revise your electrical circuits, guys, okay? Just make sure you go through your circuits now and again. The power of resistor R, the power. So remember, we're having current and resistance. We can calculate power. There's also voltage. We can use whatever that you want there, but power is simply I squared times R. We are having a current flowing across this resistor, which is 4.8 squared times that resistance of 1.25. So that was going to be the power, which is 28.8 in watts. So you can consider any formula V squared over R still, that is power again. Then we are given 7.3, an electric poster is connected to a supply of 220 volts and it draws a current of 25 amps. 7.31, calculate the electrical energy consumption for 3 hours and 40 minutes. So the energy consumption for 3 hours, 40 minutes. So remember, the energy consumption is simply power times the time. That's 7.31. That is simply the power times the time, and the time is supposed to be in seconds. So we can write this in hours. 3 hours, 40 minutes is 3 and 40 over 60, which is simply 3.667 hours. So you can convert to seconds from there. But this power, where are we going to have it from? There is voltage, there is current. So power, voltage times current times time. So that's it. So you can calculate this. The voltage is there, 220. The current is there, 25. The time in seconds. So it's going to be 3.667 times the seconds. Remember, hours to seconds in an hour, 3,600 seconds, or 60 times 60. So you multiply to 3,600. That was going to give us the energy consumption, and that is 726,066,000 joules, like that, which we can convert to megajoules, divide by 1 million or multiply by 10 to the exponent of 6 to convert to megajoules. That will be 72.607 megajoules, just like that. So yeah, that is the consumption that you're given. And 7.23, the total cost given that if the rating is 1 rand 65 per kilowatt. So for the rating, guys, you can start with the kilowatt hour. Remember, you can calculate the kilowatt hour from the concept that a kilowatt hour is simply equivalent to 3,6 megajoules, which is the energy. How many megajoules do we have? We have got 72,607 megajoules. So it's equivalent to how many kilowatt hour? So it's simply going to divide. So that is to convert to the kilowatt. So 72.607 over 3,6 times 1 kilowatt hour. That is the kilowatt hour that you're obtaining. And that was going to be 20,169 kilowatt hour. So the kilowatt hour now is the one that you use to calculate the amount, because they are saying it's 1,65 per kilowatt per each. That is one kilowatt hour is equivalent to what? To R1.65. So what about this one? You simply multiply. So the cost is going to be the product. The amount that we are given, 1,65 per kilowatt hour per one, that is per each, times the number of kilowatt hours that we used. We used 20,169 kilowatt hour. That is the cost. So it's going to be 33,279, which is actually 28 to 2 decimal place. Remember, you're talking about the cost, so it must be to 2 decimal place. So that is what you had in this case. So make sure that you do understand your information that you are given. On question number 8, which is on chemistry, we are given define an element. So an element is the substance that contains the same type of atoms that cannot be broken down into simpler substances by any chemical means. That is an element. 8.21, name the compound elements of the following two compounds, the table salt. So table salt, remember, that is the sodium chloride. So you talk of sodium chloride, water. Okay, water, that's H2O, guys. Briefly describe an element. So an element is a pure, that is a pure substance. So there we are talking about a pure substance which contains only atoms. So it contains only atoms of the same proton, of the same proton. So that is an atom is going to be of the same proton. Okay, that is what you are given there. So make sure that you do revise as much as you can. So that was it, 5 marks, a total of 100 marks in this question. So guys, let's revise for the exams that are ahead of time. Do try to work out as much questions as you can. Do as many question papers, as many revisions as you can on each topic. Question papers, full papers that can actually help you to figure out how do they ask these questions and how are you those typical questions. But that is, guys, that's how you are supposed to attempt these questions. Work more questions, like I said, till we meet again.